So generally, for robotics, we're trying to figure out the pose of the robot, and if the robot is moving on a plane, it's three numbers: x, y, and z. I'm sorry, x, y, and theta. And if it's a drone, for instance, or you want to capture the robot climbing in this dimension, it could be going up a mountain, then there's x, y, z and three angles. So 6 numbers are you're trying to obtain estimates of, and that's what localization involves. It's a state vector is made up of 6 elements. So there are 3 variations of this. This is kind of nice to know. It's in the category of general information, but it's really nice to know this. I'm a big believer that information has to be organized. You can't get into knowing what that information is. That's less important. But you have to have an organization of a field, any field, statics, dynamics, circuit theory. You have to know how it's organized, right? Before you get into the details. That organization is important. Like, it's present in other areas also, like history. They don't teach European history and then come back to Indian history and then go to South American history, right? You have different courses for the different histories. So information needs to be organized. And so this is in that category actually, because the localization problem actually has 3 variations. The third one is called the kidnapped robot problem. I'll explain why. But the simplest is what we call position tracking. So here, the idea is to determine the current pose of the robot as it moves through an update of its previous pose using measurement sensor data and odometry data, right? So that's why you call it position tracking. You have a previous pose position, same thing. So we have a previous pose and we're trying to track it as you're counting steps and you're looking up. So we start with knowledge of the initial pose. So that we start with knowledge of the initial pose. And then you're trying to track it. The simplest variant of the problem. Cabin filtering falls in this category. There are other localization methods where you don't know the initial pose of the robot. You completely start cold. Cabin filtering is not that. Cabin filtering cannot proceed unless you have an estimate of the initial pose of the robot. Is that okay? It specifically requires that. So cabin filtering also assumes Gaussians for all the, remember we said probability is uncertainty? Yeah. So there are multiple uncertainties in the case of a cabin filter, 3 of them specifically. It assumes a Gaussian distribution for those uncertainties. Markov does not, there's another method called Markov localization. You see a little bit of it. It does not assume any probability distributions. Particle filtering, no probability, because you carry a cloud and that is representative of probabilities. You carry data points in space. There is no need to use a mathematical function. Mathematical functions like Gaussian and all are creations of human beings. If we had a data that looked like a probability density function and we could afford to keep it, then we would not use mathematical functions like Gaussian anymore because we have the real thing here. You know what I'm saying? So if you had points, enough points to characterize the distribution, you would keep the points. Why would you try to make it into math functions? Well, I know why. Because when you have math functions, you can do calculus, you can derive results and so on. With points, it's kind of hard to do math on it, right? But nowadays, people are doing everything with points, Okay. Now, the global localization problem is the second variation. It's called the wake-up robot problem. We'll see why. Here we assume that we do not know the initial pose of the robot. So Calvin will not work on this problem. Yeah. We assume that we do not know the initial pose of the robot. So, what is the best distribution to capture the initial position? A uniform density. Because if you don't know, you say it has to be somewhere on this earth. Well, you don't have to say the earth. Maybe your robot has not left VIT campus. So then you assume a uniform distribution over the VIT campus, right? Yeah. So x, y, theta, each one of them, it could be anywhere here, it could be there, but equal probabilities. Same thing with y, theta, it could be any one of these, angles. So you start by assuming it has to be somewhere on this campus, and since I don't know anything, there's an equal chance of every possible x, y, theta combination. That's what they're saying. There's an equal chance of every x, y, theta. The robot needs to be able to localize globally within the environment. That means within VIT campus, right? Typically, we don't have a problem where we need to localize on the world. You know, localize within VIT, right? Because you know where the robot is generally. So, the robot needs to be able to localize globally within the environment in which it has been placed. Once it does so, it becomes this. So, this is only different in that you have to figure out that first. Uniform does not help you because it's saying I don't know, so I'm going to assume that it could be anywhere with equal probability. Then when you find out, when you have a better idea of where it is, it goes back to this problem. So the only difference is how do you solve that initial uncertainty? How do you figure out where it is initially? It is more difficult then, right? Because there is the extra part to figure out. You don't know where it is initially, you assume uniform just to get started, and then you have to figure out where it is, at which point it becomes A. So it is more difficult than problem A. This is the hardest variation. It is a kidnapped robot problem. A robot that is aware of its localization. You're saying, oh, no, it's easier. Why is this the most difficult? It is assumed to be kidnapped. So kidnapped literally means somebody picked up the robot, it thinks it knows what it is, where it is. But you pick up the robot, right? It still thinks it is in the old position. That's the difference. So it's being misled, right? Now you're saying, if I get kidnapped, I think I'll know. No, imagine you're in a deep sleep and they are very soft. They don't shake you or anything. They just pick you up gently and move you. So that's what the kidnapped robot problem. Because it's more difficult because it thinks, hey, I know where I am, right? So it's called a kidnapped robot problem. So it does not realize it's been kidnapped. Somebody just puts it somewhere else. The best example I can give is, you know, we have these big chunks of ice breaking away in Iceland and so on because of climate change, right? So let's say you're sleeping on a big piece of ice and then at the night it broke. You thought you were there, but now you're floating miles away. So that is the equivalent situation. It's literally like kidnapping. You still think you're there, and that's going to confuse you more than category B, because category B you say, I don't know where I am, right? Yeah. That's more knowledge than saying, I think I know where I am. So that's the difference. This is the most difficult category. So robot and ice flow. So the most difficult problem. So in the textbooks you'll find how they solve this and this. And of course there are many solutions of this. Position tracking is the easiest. Carbon filtering is the leading method. Alright, now we move to carbon filtering 1. So we're going to approach this topic in 2 steps. In the first instance, we are assuming that we are only applying Bayes' theorem. Look up, look up, look up, look up. Yeah. So remember the Bayes equation? Yeah. So we're only doing that part of it. The robot is not moving, in other words. Okay? And that will be meaningless, except that this is a learning style. We want to tackle the problem one step at a time. We want to first understand the lookup, also known as the perception update. The counting steps, which is known as the action update, that will come in carbon filtering 2. Is that okay? Yeah. So we are attempting it in 2 steps only because that's a good way to learn it. You know, if you throw it all in, it'll be confusing. So right now it's as if the robot is sitting there, and we are constantly measuring its position by GPS, let's say. So we're taking GPS reading after GPS reading and updating the position. And each update will give you a different result because GPS is going to be like this, right? Each GPS reading is going to be, you know, GPS readings are not repeated. Nothing is repeated in the real world. We think it is. So I take the temperature of this room and I take it again. And you're saying it's showing the same thing. That's only because they're not showing you enough decimal digits. If they show you more decimal digits, you realize that every time you take a reading, you get a different measurement. So instead of saying the robot position is fixed, we're going to switch it to a resistor measurement problem, because it's a classic problem that you have MATLAB programs, Python programs illustrating. So I have a resistor and I have an ohm meter. The ohm meter is not 100% accurate, and the resistor, the manufacturer told you it's 100 ohm resistance. You know the color code? If you remember your circuit theory, you know, at some point you went to a lab and used the color code of a resistor. So the color code there's a tolerance band. So even if it's 100 ohms, there could be like a plus minus 3% or 1% error. So there's a resistance with its uncertainty, 1% error, and then the meter is uncertain, but we're going to measure the resistance over and over again. And this is just to get the lookup part of the method resolved. Then we'll do the other part, which is counting steps. And then we put the whole. So just a reminder that the action update, which is counting steps, could also have been done by IMU, which is also like counting steps in a way. Because remember, the IMU is typically an accelerometer, which can give you acceleration in the 3 directions. And if you integrate acceleration, you get velocity. If you integrate velocity, you get position. And so therefore, theoretically, you can integrate and figure out how much you moved since your previous reading. So IMUs are also noisy though. It's not perfect. So if you use it for too long, just like odometry, it will fall apart.
So that should be more accurate.
I don't think that you can say one or the other is more accurate. It really depends on the situation. Because here's the thing, the odometry is being directly influenced by bumps on the ground. So if the right tire hits a bump, the IMU is not really affected that much by it, but the odometry will respond to tire pressure. If you have one tire that is more inflated in the left, odometry is going to be a problem. So it really depends on the situation. But both of them will fall apart eventually.
Yeah.
Odometry can only be used for vehicles that move with full rolling of the wheels.
Yeah.
So a skid steer vehicle, you skid steer, you turn just by spinning the right wheels. There's no steering wheel in a skid steer.
Yeah.
So you spin the right wheels like a tank faster than the left, and you go like this. But there's a sliding motion. So how do you know that tomorrow I don't do the same thing and you end up with slightly different position? Maybe you have loose soil here. If you have loose soil, you won't end up in that position. You'll be short, right? If you have hard ground, you might go past that point. So IMU is the only option for skid steer vehicles. Odometry can only be used where the tires always roll, that there's no skidding. So what happens when somebody comes and pushes the vehicle from the side? Well, then the odometry is useless. Because if you can push a light vehicle, right? You can drag its tires. A differentially steered vehicle is meant to roll.
Yeah.
Meant to roll is not the same thing as that it will always roll, because somebody could come and push it from the side.
Yeah.
So that means that previous odometry, it better be reset, because it's no good. Maybe you moved it 1 meter to the side, so that previous odometry is, you have to start again. It's like you're counting steps and somebody picked you up and put you there. So now your step count has to be reinitialized, right? Okay, now the perception update, that's the Bayes theorem. We're going to use Bayes theorem for that. Can come from a camera or LiDAR or GPS. There are many, that's why you have different versions of Kalman filtering as well as SLAM. Because the perception update can come from a camera, or it can come from a LiDAR, or it can come from GPS. So GPS is the most convenient, but the problem with GPS is that it's not available indoors. So if you have a vehicle moving indoors, you can't look for a GPS reading, because if you have a roof, then GPS is gone. So you have to use a camera or LiDAR. Which one is used is often a question of design philosophy. I told you that Tesla, Elon Musk's company, they don't believe in LiDARs at all, because LiDARs in bad weather can give you false readings. So if it's heavy snow or heavy rain, you'll get readings that are not reliable. So he uses only optical cameras. He has multiples, there's probably 3 or 4 cameras, but they have managed to use computer vision to get a reasonable result using cameras alone. He forced the company to go in that direction, because he said LiDAR is not the answer. He's probably right, because our eyes, right, are like cameras, and that's how we figure out where we are as we're driving, because we're looking around at features, even as we keep an eye on the speedometer, mileometer, right, how many miles, right, but we also look like, that is old, because now we have GPS direction, so you don't really do that. But in the old days, if somebody would say there's an exit 50 miles from here, so we check the manometer and then we'll be looking for an exit, right? So that's the same thing as counting steps and looking up, right? So that was in the old days. Now you have Google and so many other map systems that you don't do that anymore. So it is based on probabilistic techniques. They can't be straight averaging, or you say, okay, I'll give this weightage 67% and this 33%. You can't make up those numbers. It has to be formalized, and that's what the Bayes theorem does. It gives appropriate weightages to the counting steps part as well as the lookup part. So Markov localization, it tracks all possible robot poses. Now it's really not all, because you're not tracking robot poses in Chennai when you know your robot is inside the campus. You may not even be tracking robot poses in all of the campus, because you don't have to look at the number of tiles that you get in all of the campus. Huge. So maybe you keep 100 positions. 100 positions will be like, that's not a lot of space. It's 10 by 10 tiles, right? So maybe you only keep those probabilities alive in Markov. In Kalman, you only keep one probability alive. That's why you can't afford to lose it. You have to maintain that one probability. Because of that, there's not much computation involved in Kalman filtering compared to Markov process. But Markov keeps a little bit more. If you want more certainty, you can keep 200 alive, right? But nobody keeps an infinite number, right? The more positions you keep alive, the costlier it's going to be for you. So we are only going to discuss Kalman filtering, but I'm going to give you a glimpse of Markov localization through another document that I posted. So Markov is inefficient. See, inefficient is in the mind of the beholder. If you want a lot of confidence, then you have to be a little bit inefficient. That's always the case. You have to do more computation in order to get certainty. So that's a trade-off in life. Inefficient, maybe the inefficient is the wrong word to use there. It's more computationally intensive. Maybe that's what is the right word. Not inefficient, but computationally intensive. Because you're comparing apples and oranges. When you compare Kalman and Markov, it's apples and oranges. So one is not inefficient compared to the other. It's just getting more confidence in the process. So Kalman filtering, excuse me, tracks a single robot pose using Gaussian. See, it assumes Gaussian. In Markov, it doesn't assume anything about the probability density. You'll see when you get to that other document. So particle filtering, a cloud of points used to represent probability density functions. So basically, you're carrying a cloud in the form of points, right? You don't care about Gaussians, because you say, I'm just carrying the cloud, so I don't need any equations. So this is the one-dimensional Gaussian. You may remember it from a probability class or from high school, some high school math class. I'm not sure if they teach probability. Here they do. Here, meaning in the US. In many of the elite schools they do. They bring in probability. So other names for this distribution are normal distribution, bell curve. So it governs most statistical phenomena in life. So most statistical phenomena in life are governed by the bell curve. Things happen to naturally fall into a Gaussian distribution. So for example, if you take the heights and weights of individuals on this campus, right? Now that's different from a campus in the US, because there they tend to be bigger and taller. But I'm just saying that heights and weights here on this campus will follow a Gaussian distribution. In Chennai it will follow a Gaussian distribution. In the whole world, yes, it will follow a Gaussian distribution. But you can't take Chennai campus and bring like 100 Americans, because that's not enough of a sample to create a Gaussian, because you need more of them. So the whole world will be Gaussian, right? And then if you take the north of India, they tend to be a little bit taller. So the distribution is still valid. The distribution is a general rule, that is valid for many natural phenomena. Okay. So the beauty of the Gaussian is two numbers for the one-dimensional case, mu and sigma squared, essentially nail down the whole thing. So sigma and mu, and here sigma also again. So the reason they call it a bell curve is because it looks like a bell. The normal, because they're saying that most things in the real world are, obey this distribution. So that's why normal distribution, because this is the most common, is what they're saying. So So this is what it looks like. Let's take up this one first. So by the way, he stops here, but the curve goes on and on and on and on. Ultimately it reaches zero far, far away. Similarly, it reaches zero on the other side, far, far away. But they typically focus on 1 or 2 sigmas. So the mean is something like, whatever this number is, 1180, right? And then you have, I believe, 1 sigma, 2 sigmas. And he's showing that 58% of the population will fall within plus minus 1 sigma. And then it goes up, that number goes up very quickly, so that really nothing is happening in the wings of the Gaussian. Not much activity in the wings of the Gaussian. Most of it is happening in the middle.
Yeah.
It's important to distinguish between 2 different things here. So this is the Gaussian distribution, but if I want a sample from that distribution, right? That's not, so a sample from the distribution will be generated if I randomly get a number along this axis. So this number, the probability of generation is this much, right? That number, the probability is this much. So the distribution is one thing, but drawing a number from that distribution is a different thing entirely. This can be plotted because anybody can plot using MATLAB, this function, right? And you'll be able to generate all these curves. But a sample from the distribution is different. It's the reverse thing. You're saying, give me a sample from that distribution, right? So maybe it lies here. Give me another sample. Give me a third sample. Give me 10,000 samples. Now you can plot those samples in the form of a histogram. Most of those will fall in the middle. Fewer will be in the bars of the histogram left and right. So, but in MATLAB, if you keep on asking for samples and collect, let's say, 10,000 points and draw a histogram plot, gradually it will start to look like this. If you take many, many samples in the distribution, eventually it will start to take this shape. If you draw just 10, it will look nowhere near a Gaussian. Maybe 100, maybe not. It may not do it. 1,000, 10,000, it gets better and better, and it becomes the continuous curve. Not quite, because 10,000 is not infinity. If you are able to draw an infinite amount, then you'll get a beautiful smooth curve, just like this one. So that's what I mean by a distribution. The sample drawn from the distribution, if you do it many, many times over, you will get that bell curve. The point being that there's not much chance that you get a point here. Very low, right? So if you want to get this parts of the curve, isn't it true that you have to do a lot of experiments to generate enough points in this area? In this, here? Most of the points are going to lie here. So you have to do a lot of work in order to, get that. Okay, now let's focus on the figure on the left. So there is a comparison to be made between the blue, the red, and the yellow, because all three have a mean of 0, but they have different standard deviation. The yellow, so standard deviation is sigma, right? Sigma squared is variance. Variance is square of the standard deviation. So the variance is 5 for the yellow. For the red, it is 1, getting smaller. And for the blue is 0.2, getting even smaller. Notice what happens to the height of the Gaussian as you reduce the variance. It went from flat to slightly sharper to quite sharp. So if you continue that process, eventually you get this to be very tall and thin. So if you are using a Gaussian to characterize position of a robot, you would rather have something like this than this, because it shows more certainty. You want the Gaussian to be uncertain, because all Gaussians, it's given that it's uncertain. But you want them to be narrow and tall rather than short and broad. Broad means uncertainty. You're going to see in Kalman filtering that when you count your steps, you start off with fairly decent knowledge of your initial position, but gradually it becomes more and more uncertain. And finally the Gaussian will become flat. That means you're getting lost. And then along comes the Bayes theorem. It will pick up the Gaussian again. Then you start walking again, it gets flat, 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 flat. Then you get another GPS reading, you sharpen it. So that's what is going on in cabin filtering, Markov filtering, anything. As you walk and count steps, you're becoming more uncertain. The uncertainty, that's a human concept, right? You're becoming, I don't know where I am, is modeled by a Gaussian getting shorter and fatter. Don't let it disappear, because then you've lost position, you can't do cabin filtering anymore. So at that point, you have to get a reading. Immediately the Gaussian will pick up. And then you say, okay, let me walk some more. So, and this one just shows that basically the mean can be anywhere. That's all it does. The mean doesn't have to be 0. You can move the Gaussian anywhere. So cabin filtering tracks just one robot position carefully, because the consequences are being wrong. Because if you miss it, then the cabin filtering is gone. Unless you figure out, you at that point you become, remember the 3 problems, the 3 variations of, you jump into the second category. Right, remember that? There were 3 categories, the last one was kidnap robot problem. The second category, the moment you lose position, you jump into the second category. Cabin filtering doesn't work there. You have to again set it up by using some other means of, figuring out where you are. So it's also called sensor fusion or multi-sensor. Multi-sensor because you may choose to use odometry, IMU, camera, LiDAR, many different things. GPS. So there's a GPS slam. V-slam is, optical camera, visual slam. So there are many variations, and now I told you, I don't know whether I told you, there's a Bluetooth based slam. So within let's say a hall where a party is going on, and you want to track somebody, you can using Bluetooth slam. So all kinds of variations are possible. There is a Wi-Fi slam also. I get confused because there are 2 groups of students. So if I've told you the story before, I probably haven't. But there was a woman in, I think, Montana 2 or 3 years ago. She was driving late at night. There was snow all around in the middle of winter, and her car went off the road. Luckily, her cell phone still had power. She was knocked out. The car was damaged. Whether she was knocked out or not, she's not. She comes out of the car, she'll freeze to death. So they located her through Wi-Fi slam. So somebody said, she was supposed to arrive at this time. She's not there, and through the cell phone towers, they were able to locate, where the signal was coming from. So the cabin filtering is implemented such that one can live with the assumption of a single. That's the beauty of cabin filtering. It works because you're able to use the assumption of a single estimate. So therefore, don't let it go. Don't let that single estimate disappear, because the cabin filtering is dependent on that assumption. And yet, it's the most popular, right? I told you, cabin died only about 12, 13 years ago. It's quite old, but it was an immigrant from Hungary to the US. One of the greatest electrical engineers known because of his achievements. So we're going to go with the static case. State of the system assumed not to change. Example, robot not moving. Or resistor whose value is not changing, but you're keeping on measuring it. So it's a one-dimensional variation of the problem. When we consider motion, then in the next cabin filtering part 2, we'll assume the motion is simple. We'll assume it's moving down in a straight line. Right now it's not moving, so it doesn't matter. It's only in one position. But when it's moving, we'll assume it's moving in a straight line, just to keep the understanding easier. Because we don't want to jump into the multidimensional problem as the matrix formulation for cabin. So matrices, I know, is a weak subject for many people, and so we don't want to start with that. So here's the problem, not the one-dimensional robot localization, but an equivalent. Consider a 100 ohm resistor with tolerance of 1%. So that's the tolerance band. The manufacturer tells you that my resistor has a 1% standard deviation, sigma. So true value of resistor not changing between measurements. That's why we call it static. All we're doing is we're keeping on measuring it because we have nothing else to do. So we measure multiple times. So measure resistance repeatedly using ohm meter with error of 3 ohms. So that means standard deviation sigma is 3 ohms. Now, this is probably a bad choice, 1%, because 1 if you square it is also 1, right? So sigma squared and sigma are the same. So it should have chosen a value that when you square it you get a different number. So I said that Kalman filtering assumes that all the uncertainties, there are 3 of them, right? We get to them. All the uncertainties are modeled by Gaussian functions, right? But we also make other assumptions. So when you formally derive Kalman filtering, these assumptions will be listed. Successive measurements are assumed uncorrelated. That means they have no connection. So independent and uncorrelated are two different things. Independent is the stronger criteria. Uncorrelated is like a softer criteria.
Okay.
It's enough if the assumption is uncorrelated. It doesn't have to be independent. Just that there's no connection, no correlation between the two. Okay, so some terminology to get going. X is the actual resistance value. Okay? So we are trying to find out what X is.
Yeah.
So that is the true value of the resistor, right? And the true value can never be known. So when you have set model state, it's kind of a different situation. Because the gazebo simulator knows where the real robot is. Right? In the real world situation, the true value is never known. So how do you figure out the accuracy of a localization method when you don't know what its true value is? Now you're saying that, hey, I see the robot sitting here, so why are you saying that I don't know it? No, you don't know it precisely. A human being is able to get away by saying that, oh, the robot is here, right? But a computer, let's say we take this robot, it's autonomous, it's going through a minefield. Can you imagine? It has to be accurate, right?
Yeah.
Depending upon how closely they put the mines, the localization, you can't just say the robot is here.
Yeah.
If it's going through a minefield, you have to precisely know, you're given a map of the minefield. So it has to be precise, right?
Yeah.
There can't be too much uncertainty. That's what I mean. It's all relative to the task. So human beings can do a lot of things, but even the human being cannot guide it through a minefield by just saying, I know where the robot is, right? It's not going to work. So it has to be really precise, not just I can see it and therefore I know it's there. So it has to be very precise. Okay. So X is never known in a real world situation. So the meter reading is considered to be a noisy take or measurement of the true state. So you're really trying to get an X, but you can't, because anytime you measure, it's like there is fog around the actual value. So epsilon is like a fog. Epsilon is not a precise number, because many students will say, okay, I have the meter reading, I know what epsilon is, why don't I calculate X as Y minus epsilon? It's because epsilon is drawn from a probability distribution. So if I do it again, you'll get a different epsilon, and if I do it again, you'll get a third epsilon, but all those epsilons, they obey that probability. Remember I was talking about drawing samples?
Yeah.
So in that sense it is known, but it's not known precisely as a number.
Yeah.
It's coming from that distribution. But you can't take the value of epsilon as precise. There's a difference between the two. So you cannot calculate X as Y minus epsilon. Not possible. So as I said, I like to think of epsilon as a fog. And this is true of many things in life. You're always looking at measurements through a fog. And I am looking at you through a fog. Right now, it's clear who you are, right? Who you are. But if I turn off the lights, or I dim the lights, right? There's your fog. So that's true in life as a whole. Sometimes when you're driving, everything is clear. Sometimes it's dark, night, it's raining. So the same exit looks foggy, right? Maybe there's snow. You know, what happens in the US when there's a lot of snow, the snow tends to stick to the exit signs. So you can't read it because the snow from the top, it's kind of blocking half of, it's sliding off the face, but it's frozen because it's very cold, and you can't read the exit signs fully. So that's why any reading you take in the real world is, foggy. And so you have two variances. One is the variation of the resistance. Remember we said 1%, but we can't put in 1%, it's really 0.01. And the sigma epsilon squared was, I think, 3%. I don't remember the numbers, but I think that's what it was. 3%, yeah. 3 ohms, 3 ohms from 100 ohms is 3%. So you can't put 1%, you really have to put 1 ohm.
Yeah.
Right. And similarly, this is 3 ohms from 100 ohms. So standard deviation does have a value, units. Standard deviation has units. It's not, a dimensionless number. Okay. All right. So I'm not deriving Kalman filtering, right? I told you the derivation is a matrix-based derivation. I used to do that in my classes,
Yeah.
but increasingly I felt that it wasn't achieving much for the category of students, so I started to just give them the results and explain why the results make sense. You will see that the Kalman filtering result makes a lot of sense. It is so intuitively correct, and yet he derived it formally with math, with matrix algebra, differentiation, and so on. But yet it's a method whose underpinnings, what is at the basis of that is so clear because the result is so intuitive, you can relate to it. So in the process of applying Kalman filtering, there's something known as the Kalman gain. It's named after Kalman, the great guy. The Kalman gain is defined as the ratio of these two. So these are not suddenly appearing, they are these two. So this is the ratio. So the variance of the resistor squared, remember the manufacturer said, this is my Gaussian distribution, and right? And in the denominator we have the variance of the resistor squared plus the variance of the meter squared. So that's one part of it. That gain is used in the estimate. So this is the original estimate. This is the next estimate. So you have the original estimate, you measure it.
Yeah.
And so immediately you update the estimate based on the measurement. So this is the equivalent of looking up, right? Remember looking up, right?
Yeah.
You look at the surroundings. So the measurement is put into calculating the Kalman gain, and here it is. The old estimate plus B, the Kalman gain times the difference between the measurement and the old estimate. Now, expressed like this, it is not as clear as a different way of expressing it. And that is, open up this parenthesis. So you get B times Y1, right? But you also get B times X0 with the minus sign. So I can combine the X0 with the minus B X0, and I get 1 minus B X0 plus B times Y1. Is that clear, or do you want me to do it on the board?
No.
Because essentially I can expand this and combine the two terms with X0, and so I get a 1 minus B and a B here. That is beautiful, because you're saying, let's say B is 0.3. You're saying, I'll give a weightage of 0.3 to one and 0.7 to the other. And that makes perfect sense. If you are just averaging them, you'll say 1 plus the other by 2. But for that, B has to be 0.5, right? In general, it isn't 0.5. Because step counting, you're not so sure about step counting, right? But you're a lot more sure about, okay, I'll take a LiDAR reading. So that number should not be, even. In fact, the measurement should be better than the step counting most of the time. So therefore, Kalman figured out, he actually formally derived this, and he got this result that B makes perfect sense. It takes a little bit of X0 and a little bit of Y1. But having said that, this is the form they implemented. Yeah, it's nice to split it up and say 1 minus B and B, because that's better for understanding. But in terms of implementation, this is how they do it. Okay, now this will make even more sense for this is called the update equation, the Kalman update equation. That is the Kalman gain. So first you calculate the Kalman gain, and then you apply the update equation, right? This is the looking up, the perception update. There's 3 equations here, one more coming up. These are just 2. So there's 3 equations here. On the step counting, you have 2 equations. 3 plus 2, any Kalman filtering process has 5 equations over and over again. Take steps, 2 equations. Look up, 3 equations. So 2 plus 3 is 5. Then go back and take steps again. So 5 equations, right? Simple equations, because see here, this is called a recursive equation. All I need is a previous estimate of where I was, and then I can get a new estimate. Yes, if I'm doing xy theta or xyz triangles. It's a matrix update, right? But still, it is recursive. All I need is the previous values of those quantities. And it's a simple one-step recursion. And that's why even today Kalman filtering is the commonest form of localization. It's used by all planes. Every single plane in the world uses this process because you get a GPS update, right? But in between you have to figure out where you are because the GPS comes, and these planes are flying at 500 miles per hour. So, you know what I mean? Even if GPS you think is fast, but these planes are flying at 500 miles per hour, so that's a very high speed. Once they reach cruising altitude, they go quite fast. So look at this. This is the best example of why that makes even more sense. Let's say the meter is much more accurate than accuracy of stated resistor value. What does it mean? Meter is much more accurate. That means sigma epsilon squared is much smaller than sigma x squared. Is there a meter much more accurate? Now, in our example, that's not true, right? Or is it? He's saying the manufacturer says 1%, but the measurement says 3%. That's not normally the case. The measurement is not so bad. Typically, the measurement is better than, your instrument is much better than that. So maybe I should change those numbers because you say, why measure at all, right? If the measurement is going to be worse than that, you say, why? I'm just going to count steps and go around the world, right? So, you know what I mean? Because the measurement is supposed to be more accurate than step counting. So, in any case, meter much more accurate than accuracy of stated resistor value. So, this meter is much more accurate than, so what happened is the sigma epsilon squared is much smaller than sigma x squared, and therefore this tends to 1. So that means believe the manufacturer's number, don't believe the meter. On the other hand, opposite situation. The meter is much more accurate, right? So the meter is much more accurate than, we already said that. Meter much more accurate. Then the meter is not so accurate. Then what will happen is, you will throw away this in comparison to this, right? And therefore it will tend to 0. Does that make sense? So it makes perfect sense what the extreme cases are. Most of the time B is somewhere in between. And that's how the Bayesian update. This is based on Bayesian update. I did show you the derivation, but these equations result from Bayesian update. So the Bayes theorem led to this beautiful equation, and it makes perfect sense. In any other general case, the estimate appropriately combines both readings. So it is something based on formal derivation. It's not something that he just cooked up, Kalman. So forget the ML terminology. Here's what it is. He's not saying that each estimate is the best, the first or the second or the third. Maybe you get lucky and some of the method you choose turns out to beat that one estimate. All he's saying is, if you use this method over and over and over and over again, it is the best possible method. He's not saying that you can't beat me on one estimate or the next. He's saying, if I use my method over and over again, I can show that it is the best possible method. So, as an average, it gives you the best result. So, ML estimate, which is the Kalman estimate in this case, does not guarantee that each computed result is the best. Only that on the average, the method gives the best possible estimate over many readings. Okay, now here comes the third equation. Now, again, I'm giving you this as a result because we have combined the measurement with the result of the step counting, right? X0 came from the result of step counting. We just combined it with a measurement.
Yeah.
Therefore, we have, I should use the word polluted, but the steps was polluted by the measurement. You get what I mean? You combine the two. So you have to change the variance associated with sigma 1. It's not the same thing as the previous one because you combine the old variance with the measurement variance, right? And so you have to push up your variance also. And Kalman's derivation also includes that. And the result is, you have to accept it because we're not doing the derivation. The new sigma is sigma x squared, sigma epsilon squared over the sum of the two. And this is incidental. You can show that this can be rewritten like this. And by the way, this is the form that it's implemented, just like the previous case. But let's not worry about that because this is the one that has a lot of insight. So after the measurement, you get a new variance of the estimate, right? So I look at the right hand side and say, first of all, the result is this. This resultant variance is going to be smaller than the smaller of the two. So I don't expect you to accept that because I'm just about to give you an example to show you that. So this is smaller than the smaller of these two. How do I know that? So the best analogy is, you know how resistors are combined in parallel? So this is R1, R2 by R1 plus R2, right? And do you know that the equivalent resistance of a couple of parallel resistors has to be smaller than the smaller of the two? It's a given. What happens if you combine a short circuit with 5 kilo ohms? You get a short circuit, right? But in that case, it was at least equal to 0 ohms. But if you combine 5 with 10, you will find that the resultant is smaller than the 5 kilo ohms. It's a given. It's mathematically provable. So therefore, sigma x hat squared, the hat means estimate, by the way. If you put x, that's the true value. Hat means estimate of x. So therefore, it has to get, any measurement has to make it better. So if you measure it again, you still, even though you measure twice, you still have to update the variance of the estimate. If you measure twice and you've done 2 Bayes rule applications, 2 sensor fusions, you've got to update the estimate because it's been twice tainted is not the right word, with the measurement. Okay, so here are the 3 equations. So the first thing you do is the Kalman gain. You have to do the Kalman gain and then the update and then this. It has to come in this order. You can't calculate the Kalman gain after you've done this because that gives you an idea of what to put here. So the measurement, Bn comes from here, finally you update the variance. So as I said, we're using the second form. We're using this form, not this. So what do we need to get this process started? We need the expected value of the resistance before any readings are taken. 100 ohms. The variance of this value, 1 ohm. The variance of the meter readings, 3 ohms. Then you can do it all day if you have the energy. The procedure is recursive. No need to save all of the older readings. What is needed is just the previous estimate, the new measurement, and whatever it takes to find P. So it's very simple, compared to Markov localization or particle filtering or anything. But we may come to a point where memory and computation speed doesn't matter anymore. We may reach that point. At which point, maybe people will stop using Kalman filtering. Because everything is relative, right? If you can wastefully calculate, then you do it, right? If there's no cost to that, you go that way. So MATLAB cannot be an implementation medium, right? Because MATLAB takes a long time to compute. So that's why when you have an embedded systems application, you have to figure out, can I implement the same algorithm using 8-bit number representations? That's a separate science, by the way. You have to get into fixed point arithmetic. So MATLAB does have a fixed point toolbox. So after you've done the algorithm, you can ask yourself, if I have an 8-bit processor, right, and I'm short of resources, what will I do with this algorithm? Because I can't put MATLAB on on the platform. So then the implementation issue comes up. Turns out, most of the time, you don't need the power of a regular desktop computer. It's just convenience that makes us implement our algorithms here. Most of the time, 16 bits or 8 bits or 12 bits is good enough for a lot of algorithms. But you have to figure out how to do it properly. So when the update process is executed, all of the past is absorbed into that one new estimate. You can throw away all the past. It's a one-step recursive process. So that's why it's computationally efficient. So I used to, I would tell the students to complete, I would give them like a step and a half and say, okay, keep on doing it. But I made up these numbers, like 95. Okay? So I said, hey, my multimeter gave me 95. what is the better way to do this? I should really have drawn a number from that Gaussian distribution. Me making it up is biased, right? I should really get a number, I should get MATLAB to spit out a number, and then I should have put it there. And then you can continue to work this, you can write a program, you don't have to sit and enter numbers into a calculator. But you'll find it's quite nice to see what happens to the updated sigma. It will get better and better. And now you're saying, if I do 1 million measurements, will I reach perfection? No. After a while, the returns are less. So initially it will get better. Like the first time manufacturer's value, and the first measurement you'll get the maximum improvement. But after that, when you go on measuring, it tends to saturate out. It has to be that way, right? Because what else could you get, right? So after a while, you don't get any. But remember, the real world, you're also walking. So the walking blows it up, right? Because if you take 100 steps, or maybe the GPS failed for some time, and now you walked 1,000 steps. So now you have a lot of correction to do. So you don't sit and measure the same thing over again. That's my point. That in practice, you need the measurement. The measurement saves you actually. Okay, so now we're going to move on to dynamics. We may not move to dynamics in the morning because I have some other things to show you. But I'm just setting up a part, which is the step counting. So if I were to continue this, I'm not going to do that because we are going to flip back to the robot example. That robot that was just sitting here and we are measuring its location through GPS over and over again, it's going to start moving along the line. But I just wanted to say, if you wanted to continue this resistor example, how would you account for a changing resistor? So maybe the temperature in this room is changing. I'm just making up a story, but just keep with me. Right? So between measurements, the temperature is changing. So maybe you have a very rough equation of resistor value versus temperature. So that would be like your steps. And that's how cabin filtering is used in many places, including chemical processes. So in chemical processes, they have rough equations that tell you what is the state of some interior variable. But then every once in a while, you can afford to do a costly measurement. And you know what the measurement could be? It could be taking a sample and you give it for quick chemical analysis. Right? In between, you need some rough model, like you're counting steps, right? Odometry, you need some rough equation. So then you can extend this problem and make it a cabin filtering problem with no reference to robotics at all. So the point is, cabin filtering is used in chemical processes, many different areas. But we're going to get back to the robotics example. And this the second example. We go through it in the afternoon in detail. What else? This was a nice book I found on Amazon, probably the last copy. 4 Man's Explanation of Cabin Filtering, or How I Stopped Worrying and Learned to Love Making Filtering. So it's somewhere at my house because I squeezed everything possible out of it in terms of notes. So it's a nice book written by one of the original implementers of the cabin filtering technique, Roger Plessy. Maybe he's no more. What I want to show you. Now, I am a little bit fuzzy because of the two groups. So I'm not sure I showed you this. Maybe not. So let me just check. I want to show you these videos because localization is not always with respect. And did I show you a video where we had drones flying?
Yeah.
You saw that, right?
Yeah.
Oh, okay, good. So, I don't know why I was confused. So let's move on to something else. I wanted to show you a video that was sent by my doctoral student just a few days ago. And it kind of shows you why localization is important. So let me locate that video. It won't take long. So my student is working on multi-robot localization. So imagine that you're in an Amazon warehouse and you have different, robots. Because, you put a human driver on a robot, the cost goes up for all of us, including us. So everything is automated, and they say by 2030, Amazon will have more robots than workers. So it's a little bit scary because you would consider that a low-end job, packing. Like somebody orders this and that, you put it in a box, put padding, address label and send it. Everything is going to be automated. So right now a lot of moving is done by the robot. So it goes and finds the product. I still don't know how they pick it out, because if I order mine is a blank. Let's say you order something really small, nails to hang a picture on the wall, right? It's going to be in a bigger box with many of them. So I don't know how the robot gets just one or two, because you're not going to order 10,000. So that part I'm a little bit confused of, but that it goes and gets it, and then it brings it to an operator station, and then the operator station, that person puts it together. So you have lots of these robots moving around. So maybe kinematics, but maybe kinematics and dynamics, because they wanted to go fast, and these things are heavy, right? So they wanted to go fast. So dynamics will be involved, right? How do they get out of each other's way? Because if you want to, the Amazon workers are a group of people who are the most stressed in the world, because they're trying to form a union. That doing the same thing, right, for 8 hours is not a fun way of working. So these robots, how do they stay out of each other's way? Because they have to move quickly, because all the orders they have to fulfill, because they promise next day delivery, 2-day delivery, right, etc. So how do they do that? And then once the box is ready, you have to take it to a particular dock, because maybe there are packages that go to Chicago from their centers or to New York. So how do you keep these robots apart? So you need some kind of a trajectory planner. So a trajectory planner is different from a path planner, as you'll see when we get into the cognition topic later today or tomorrow. Path planning has no attachment of time. It just says this is the best path. Whereas a trajectory is, you tell the robot you need to be at XY at this time. So it is not, the path plan is just XY, right? XY, 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 XY. When you drive, when you drive it's actually a trajectory. But if you just look at the Google map, it says XY, XY, XY. In order to drive a robot, you have to make it a trajectory. A trajectory is XY with a time attached. So that means you have to worry about kinematics and dynamics. You have to contour the path properly. So all robots might not be able to make a right turn. So you need to give an X, Y, and T, which is an approximation of the path plan. So this is the video. So this is the central part of our building that is around.
So you showed this.
Oh, I showed you this, right?
So the
okay.
robots avoid each other and they.
Okay, so as I said, I'm a little bit confused because of the two groups. But the point was that you need trajectory planning. You don't need trajectory planning if you're willing to stick with inefficiencies. But you know what it means. You want them to move as fast as possible. I think the Amazon guys would like them to move like race cars. But that's not going to happen on a shop floor without killing somebody. So what is the best possible? Move as fast as possible. So yeah, then you don't need to see this. So you can see that the localization was very important, because otherwise you think you're here and you're going to miss that robot. Maybe you're not here and you're going to hit that robot. So that's the difference. So what we're going to do is we're going to go back and play that postgraph. So that's important enough not to skip. So let me pull it up. This is of the localization and mapping PowerPoint. So let me go get that. So this happened the last time also. For some reason, the cut and paste is an earlier cut and paste.
That's its location and orientation. If we already had a model.
Sorry, I'm going to play it right at the beginning.
In this video, we're not going to have a map ahead of time. In the last video, we talked about how we can estimate an autonomous vehicle's pose, that's its location and orientation, if we already had a model or a map of the environment. In this video, we're not going to have a map ahead of time. We're going to have to build one while simultaneously figuring out where the vehicle is within that map using a process called SLAM, Simultaneous Localization and Mapping. There are many different SLAM algorithms, but they can mostly be classified into two groups: filtering and smoothing. Filtering, like the extended Kalman filter or the particle filter, models the problem.
So we were talking about this side. Now, the category is the smoothing side. So you find it has a disadvantage. Now maybe let's watch the video and then I'll ask you what the disadvantage is.
As an online state estimation, where the robot state and maybe part of the environment is updated on the go as new measurements become available. On the other hand, smoothing techniques estimate the full robot trajectories from the complete set of measurements, not just the new measurements. And understanding these methods can be more intuitive if we address them under a graph-based formulation. In fact, in recent years, one particular framework, pose graph optimization, or more generically, factor graph optimization, has become the de facto standard for most modern SLAM software solutions. So in this video, we're going to focus on understanding what pose graph optimization is and why it works. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. Let's set up the problem. We have an autonomous vehicle, a robot, that has the ability to move through an environment. We've given it LiDAR to sense the distances and angles to nearby obstacles, and we've given it a way to dead reckon its relative position over time using odometry. In this case, it uses wheel encoders to count the number of rotations each wheel makes as it drives, and from that it estimates how far it's gone and how it's turned since its last known position.
Isn't that beautiful graphics?
Yeah.
So we didn't have that when I was a student, obviously. So, when you have something like that, it makes the task of explaining so much shorter and more powerful. If you could do graphics like this.
So the question is, how can we use these sensors to understand what the environment map looks like and figure out the robot's pose over time? Well, let's start with a simple mapping problem. Here, I've placed the robot in a rectangular room with a circular obstacle in the corner. We can see this map and see where the robot is, but it has no idea either. To it, it's just in an unknown void. Let's start with a very ideal situation, one in which there is no uncertainty or errors in the LiDAR or odometry measurements. They're just perfect. In this situation, developing a map of the environment is relatively trivial. The robot could take a LiDAR measurement, and we'd have confidence that what it measured is the real obstacle location.
So he's describing a situation that is not feasible in the real world. He's saying, let's assume that everything's perfect, right? I got perfect localization, I've got perfect LiDAR to measure distances. So under those assumptions, it's not going to be difficult to build a map.
It could save that off in a global map and then continue on. After driving some distance, which again we know precisely because of the perfect odometry, it takes another measurement. Now, the two measurements will align nicely in the global map since there are no errors in our system, and in this way we can just keep driving all around the environment and create a perfect map, all while knowing exactly where we are at all times. Of course, this scenario isn't realistic. There's error in both the LiDAR measurement and in the odometry, so there's some uncertainty in the estimated robot pose and in the distances to the measured objects. So let's try to map this room one more time. But this time we'll say that the LiDAR is still pretty accurate, but there's a large uncertainty in the odometry measurements. I don't know, maybe one of the wheels keeps slipping, so the robot thinks it's moving in a different direction than it actually is. So let's see how this works out for our robot. We get an initial LiDAR measurement, and we assume that there's an obstacle there just like before, and then we drive a little bit. Except this time the estimated pose is different than the real pose. So the LiDAR returns some relative distances to the wall that the real robot sees, but we can only assume that it's relative to the estimated robot pose, since that's all we know. This places the two
But that, because it can only assume that the view is from the odometry position, because the real position nobody knows.
measured obstacles in different frames and not a global environment frame, so they don't line up. If we continue this process as we drive the robot around the room, the error in odometry causes our estimated pose to deviate more from the real pose, and what we're left with in the end is this map of obstacles that doesn't resemble the real environment. So this is one of the reasons why we can't just take measurements of the environment and stick the results into a map. Uncertainty in our system is going to mess it up. But this is where SLAM algorithms can help us. As I said at the beginning, in this video we're going to focus on pose graph optimization. I want to provide a little intuition behind the algorithm and give you a feeling for how it works without a bunch of math. But if you want to learn more about the mathematics, I've left some great resources in the description that go through it in detail. Just like before, we have our real and estimated robot poses, which at the beginning lie right on top of each other in the real environment map. But now on the right, there's also this blank area, and this is where we're going to build up the pose graph. The first thing our robot does is take a measurement of the environment. This measurement is associated with the current estimated robot pose, and we can add both to the pose graph. So essentially what we're doing is saying that this pose is defined as an X and Y location and a rotation angle. And along with it, we save off the distances and angles to the sensed obstacles. Now, there's also uncertainties associated with this pose entry, but I'll get to that in a second. All right, so we have our first entry in the pose graph, so let's get the second. Again, the robot drives for a little bit, and our estimated pose starts to deviate from the real pose. Another measurement of the environment, which gets associated with the new estimated pose, and this combination is now saved in the pose graph. So we have two poses, each with their own local estimate of where the obstacles are. And even though we don't know where these two poses are in the environment, we do have an idea of about how far apart they are from each other. In our case, this knowledge came from counting the wheel rotations, but the idea behind this SLAM algorithm isn't tied to a specific set of sensors. The relative pose distances could have come from another internal measurement source, like an IMU, or we could have figured out how far the robot moved from other external sources, like GPS or visible odometry. The point is that we have some best guess as to how far away these two poses are from each other, as well as a measure of how confident we are in that guess. In this way, there's a constraint that we can place on the relative distance between these two poses. Ideally, they would stay exactly this far apart, since that's our best estimate. But due to our uncertainty in the odometry process, maybe we'd be better off if we moved these two poses around relative to each other. For example, it would be nice if there was a mechanism that would be able to move the two poses around to align the currently misaligned obstacles.
So, the features that you're seeing, right? There is some relationship between them, you know. So, in other words, you're seeing the same wall segment, for instance. So, if the wall segments have to be the same, which they have to be because it's the same wall, then can we use that to figure out better where the robot should actually be? So the math has to obviously be brought along, right? But basically they're aligning features of the same aspect of the environment and then seeing whether that can improve their idea of, you know, where the robot actually is. Because odometry is putting it in two different places. It's come all the way around and it's looking at the same part of the environment.
Well, there is, and the constraints are the key to doing it. To visualize a constraint, I think it's helpful to imagine a rubber bar connecting the two poses. The nominal length of the bar is how far apart we estimate them to be. And with no external forces on these poses, the bar will just keep them at this fixed distance. However, if I hold one pose fixed and move the other pose closer to or further from it, it will compress or stretch the rubber bar, and there will be a force that wants to restore the poses back to their nominal distance. And the strength of the rubber bar depends on how confident we are in the distance estimate. If we have more confidence, or we have a really good odometry process, then this is a really strong bar that makes it difficult to change this nominal distance.
That's the thing. If you're super confident about the odometry, you will have to ignore the fact that the walls are falling at different places, right? But you know that's not true. You don't have super confidence in the odometry. So if you rely on the walls, you can bring the odometry together better.
If we have almost no confidence, then this rubber bar is very weak and provides almost no restoring force. So in pose graph nomenclature, we say that the poses are the nodes of the graph, and the constraint, or the rubber bar, is an edge. Of course, this constraint acts in all three pose dimensions, both x and y, and in rotation. always trying to bring it back to its estimated distance. All right, so there's not much we can do with 2 nodes and 1 edge, so let's keep going. Just like before, the robot keeps driving along and measuring the environment. And after a measurement, we can take the estimated pose along with its measurement of the local obstacles and place it in our pose graph and add a constraint. So now we have 3 nodes and 2 edges, and we can continue.
So this graphical picture is happening through representations, The graphics is just to explain it to us, but the mathematics is going on internally on the graph created, which is just numbers. So we don't have to draw, the computer doesn't understand anything that's drawn. We have to tell it what to do with numbers. So this representation is only for our purposes.
Continue this, filling out our pose graph 1 pose at a time until we have something that looks like that incorrect map that we built earlier, with the exception that there are these constraints connecting all of the poses together. We still can't do much with this information because you can imagine that all of the bars are at their nominal length and everything wants to stay right where it is. However, we're at a point where something interesting can happen. Our first pose and the current pose are both observing the same feature in the environment. This means that we can build a new edge, a new constraint between these 2 nodes. We just need to understand how these 2 features align to figure out where the 2 poses have to be relative to each other. And in this example, they would have to be in the exact same location. So now we can add a new constraint, one that connects the first and last poses together and closes the loop. This bar has a nominal length of 0, since these 2 poses want to be right on top of each other. And the strength of this rubber bar depends on how confident you are in your external measurements and your ability to associate the 2 sets of data as the same feature. If you're really confident, like we are in this example, this bar is extremely strong. It really wants to pull these 2 poses together. So hopefully you can start to see that a loop closure is the thing that makes all of this work. Without a closure, all of the constraints were just happily being met. But with a loop closure, we have a way to inject tension into this graph. The blue bar wants to pull those 2 nodes together, and the purple bars all want to keep the relative distances the way that they are. And so allowing this graph to settle to equilibrium, or to balance all of the forces that each of the constraints are imposing, is the optimization part of pose graph optimization. And what's really cool about this is that by optimizing the pose graph, not only do we have a better estimate of the current pose and a better model of the environment, but we also have a better estimate of where the robot was in the past, since all of the past poses were updated as well. So we got a lot of value from this 1 loop closure. Of course, you can see that we don't have a perfect model of the environment or the robot poses, but that's okay because we can continue to improve our estimate by making more loop closures. The robot can continue to drive, adding new poses from odometry and new loop closures wherever it's able to determine a relationship using external data. And for this example, let's assume we were able to...
So you don't do it just once. You do it many times because, there are other parts of the environment where you may spot something familiar that you have seen before. So that's the key. Have I been in this part of the room before, right? It looks slightly different. So you can use that for a loop closure.
To relate these 3 poses together, even though this area of the room is relatively featureless. At this point, all of the previous constraints are the same as they were before. And until we added these loop closures, the graph was still in equilibrium. But now we've added new loop closures, and this has created more tension, which wants to tug and push on all of the other poses a little bit. And so we need to rerun the optimization again and allow the graph to resettle. In this way, you can see how after each loop closure, the graph will continue to improve its global model of the environment and the past robot.
So, important thing, not to get carried away, because it's not, the final result is not going to be perfect, because you cannot get perfection in this world, right? But it's better than just using odometry to map, because we have tried to map with odometry. The map is all over the place. It is unusable. Basically, it's unusable. You have to have better localization. So The thing is, can you get a system in place that has a smaller error? That's what you're looking for in the real life. There's no such thing as no error, but smaller error, right? Because remember, the LiDAR, he assumed in the beginning that the LiDAR is perfect, right? But the odometry is not. That is only because he wanted to simplify the explanation. Both of them are imperfect. One is a little bit more perfect than the other. Remember the Kalman filtering? Like steps is not good, but the GPS is better. So you have two imperfect processes, and the theory shows that you can end up with a better estimate that you can live with. That's the whole point. Because people are building maps now. Self-driving cars, they have to have good maps, because otherwise they will hit all the other vehicles around them. So that's the point. Now, we'll finish the thing, because there's an interesting piece on mapping there. But I asked you at the beginning, is there a disadvantage that you see to the post graph versus the Kalman filtering approach? Remember the smoothing versus the estimation? So here, you have to come back and see something that you've already seen, right? But if you're in a battlefield situation, who can afford to do that, right? So the other method works when you have to keep on moving. This method has to be used can be used when you have the luxury of going back. So let's finish up the video here.
Poses. That is, as long as the two poses that you connect are truly looking at the same environment feature. If you make an incorrect association and you build an edge with a constraint that is not.
So that's another thing. If you're unsure that you're seeing the same thing, he says don't use that data. Because if you use it, then it's like sliding backwards. So you have to be sure that you're seeing the same thing. That's not easy, right? Human beings think it is easy. I can show you two traffic barrels and they will look exactly the same. Maybe after much usage you may notice that one of them has a dent because somebody hit it, but those things are hard to find like that, like most of the time they will look alike. So, I can show you paintings that look exactly alike. So I think I may have mentioned that if you want to localize in a long hallway, if the hallway has no features, no hanging painting on the wall, but what if I put the same painting? That's no good either, because it's going to confuse you, right? So if you put different paintings, then you can do it.
Real, you can imagine how this would persist in your graph and continue to skew your optimization process every time you run it. It would always be pulling those nodes in a direction away from the truth. So it's incredibly important that you are confident in any loop closures that you make. In fact, it's better to miss a real loop closure than it is to add a false one. You can always drive around some more and make another closure in the future, but it's harder to remove the bad ones once they're in. Now, it's also important to note that a loop closure requires an absolute measurement of the environment, like we got with LiDAR, or you could get with a visible camera or some other environment sensor. You can't close the loop using a relative sensor like an IMU or the wheel encoders, because there's no way to relate that information back to an older pose. You may think you're near a past node, but without checking the environment, you can't know for sure. Okay, so we have our pose graph and we've optimized it. Now, how do we build a map of the environment from all of these data points? Well, there's several different ways to represent an environment model, but I'm going to quickly introduce the binary occupancy grid. The idea behind it is that the environment is broken up into a grid of cells. If you believe the cell is occupied, you set the value to a 1, and if it's not occupied, you set it to a 0. Here, I'm assuming the entire environment is empty, and then filling in the cells where I believe there is an obstacle. But you could also assume the opposite, where the cells are all occupied and you set them to 0 when your sensor indicates that there's nothing there. You can see that with just 1s and 0s, we've generated a pretty accurate model of the rectangular room and part of the circular obstacle. There are some holes, and we can fill them in by driving around a bit more, but overall it looks okay. Now, there's also probabilistic occupancy grids, where the cell doesn't have to be fully occupied or not, and instead there's a probability that it's occupied.
So if you go with the binary mapping scheme, it's absolute, and you cannot place and remove moving obstacles. in your scene. In order to remove moving obstacles, you can't have an absolute 0 or 1, right? Because you have to sample that tile. You have to sample the space over every tile, and therefore you have to have gray level mapping. So imagine at each one of those positions, you have an 8-bit number. So there are 256 possibilities, right? So every time you see something over that tile, you up count. You say, I saw it, I saw it, I saw it, I saw it. And then it's no longer there, it's no longer there, it's no longer there, down count. So if you want to be sure, it may not reach the level of black, right? So you have to make a decision. So you set a threshold and say if it's greater than 128, I'll assume there's something there. So that's how in practice a machine is being forced to think like a human being. You know, that's the best we can do because the machine is not a human being. But they have these gray level maps, which is called the probabilistic occupancy gray.
Between 0 and 1. With this model, you have full confidence in black and white cells, and everywhere else is some shade of gray, depending on your uncertainty. So there we have it, SLAM using pose graph optimization. Hopefully now you can see how a map of the environment and the pose of the robot can be determined simultaneously with this method. And now that we have an occupancy grid map, we can start the process of planning a future trajectory through this environment. The robot no longer has to wander around aimlessly, but can use this map to plan where it wants to go. And we're going to cover some ways to approach planning in the next video. But before I end this one, I want to remind you that a great way to learn this stuff is to just practice it and try it out on your own. There's a MATLAB example that uses the navigation toolbox called Implement SLAM with LiDAR scans that builds up an occupancy grid map of the environment using just LiDAR. No relative odometry process required. Essentially, the environment has enough unique features in it that the LiDAR measurement of every pose can be related back to other past poses just through data association or feature matching. It's worth checking out and playing around with. And I've linked to another video below that walks through this exact example if you want more information. Okay, that's where I'm going to end this video.
All right.